Yes, thank you, Anna, and also thanks to all the organizers for giving me this opportunity to present you today. I would say a combination of experimental and theoretical results concerning the dynamics of nanometric reactive systems. So as you were saying, I'm from Brussels, and so experiments and theory were done in Brussels too. But by two different teams. So the experiments were done by Cédric Barrault, Thierry Vizard de Bocarmé, and Norbert Cruz, who is now at Washington State University. And the theory was done by Pierre Gaspard and Valérie Vauxleus, who is now at the Université de Luxembourg, and by myself as well. And so in terms of context, okay. In terms of context, so the idea is to study complex chemical processes. As you all know, probably, chemical reactions can give rise to very complex phenomena out of equilibrium. And these complex phenomena can be temporal oscillations, like in the Belousov-Zhabotinsky reaction. Here you have a few examples of evolution in time of ions in a well-stirred aqueous phase. But for systems that are not stirred, you can have more complex spatio-temporal phenomena like spirals, target patterns, or what could be described as chemical flowers, as we can see here. So in terms of theory, usually this whole complexity is explained in terms of the kinetics of the reaction rates. So the concentrations involve reaction rates that are nonlinear in the concentrations. And this means that the evolution equation for the concentrations give rise to ordinary or partial differential equations, and they can be studied with the whole arsenal of the theory of dynamic of systems, stability analysis of fixed points, analyzing phase space trajectories, and so forth. And this approach has been validated against experiments on a really large number of cases. So we can have some confidence in the results of this kind of approach, but the problem somehow is that these laws are valid for very large populations of molecules in terms of numbers like the Avogadro number of particles. But the development of nanotechnologies and biotechnologies has led to the question of what could happen in much smaller systems. So do these complex phenomena still exist? What is the effect of the fluctuations that appear at such scales? In such case, obviously, stochastic approaches are needed, usually based on master equation or Langevin equation. I will talk about that later. And these approaches give a whole lot of predictions on how fluctuations affect dynamics like oscillations, for example. And contrary to the macroscopic case, I would say, there are not so many experimental verifications of the predictions of the stochastic approaches. And the whole point of the project I'm going to talk about today is to have some sort of experimental validation of the predictions of stochastic theories in the case of reactions. And the idea is to combine nanoscale experiments done with atom microscopes and predictions of the stochastic theories to assess the range of validity of these theories. So we did very many different things, but we only have 20 minutes, so I will present maybe one or two examples of what can be done or verified. But before I can do that, obviously I need to say a few words about the experiments, because there are not so many experimental techniques that allow one to follow in real time the dynamics of reactions at the nanoscale. And the experimental setup that we have been using is called the field emission microscope. So the principle is not very complicated. So one has a sample that is usually a metallic tip. So it's like a very thin needle that is called the specimen on this graph here. And this is placed in a reactor at very low pressure. And in front of this sample, one places a metallic plate that will play the role of a counter electrode. Because yes, the difference of potential would be applied between the sample and the counter electrode. And if this voltage is sufficiently high, then electrons can be ejected from the sample. And since the trajectories of these electrons are diverging, what one can collect at the level of the counter electrode is a hugely magnified map of the current distribution at the level of the sample itself. So what is important to remember here is that current is collected at the level of the counter electrode. And this is very interesting because the current, if one agrees with this equation, which is called the Fowler-Nordheim equation, this current is directly related to the work function. So the work function, if you remember, is the energy needed to eject an electron from the bulk of the material. And so this work function depends on the material itself, on its structure, but also on the chemical composition at the level of the surface. So if a metal is covered with molecules, this will affect the work function. And so this will affect the current emitted by the tip. And so since the currents can be converted in images, what you will see are images where you have different brightness at some places, and the brightness is directly proportional to the current. So this means that variations of brightness in the images can be related to variations of the chemical composition on the surface. And so as I said, I don't have so much time, so I will focus on one example, which is the case of oscillations that we have been observing in the NO2 plus H2 on platinum system. So in this case, we chose platinum because platinum is known to be a catalyst for reactions involving NO2 and H2, which means that if we put all these things into contact, we can expect to see something. Moreover, since it is a catalyst, we can expect to see something under relatively mild conditions. This means that we can use low pressures for the reactants and relatively, let's say, acceptable temperatures like 400 Kelvin, for example, and we can expect to see chemical reactions going on. So on the left-hand side here, you have an example of what a FEM image looks like. So FEM is field emission microscope. So you see some sort of blurry contrast of brightness. So sometimes it's brighter than at other places. And to understand what it means, this can be compared with an image obtained with a connected but slightly different technique, which is called film. But this is not really important right now, because film has a resolution which is of the order of an angstrom. And so the two images are the same sample. And so this means that we can associate to different places in FEM, locations in film. So in film, all the dots that you see are atoms of the metal on the surface. And so with this comparison, we can say that what you are going to see is something which is approximately 50 by 50 nanometer. So this is something like 10 to the 5 surface atoms. And I will also show time series of the brightness, and the brightness has been recorded in an area that is even smaller, which is 8 nanometers square, which is in pink or red, depending on the picture you're looking at. So what we do is perform experiments by observing what is happening at constant pressure and temperature. And this is what we see. So everything is constant in terms of parameters, but nevertheless, the brightness, and so the current emitted by the tip, is oscillating in time, which, given what I said before, also means that more than probably the chemical composition on the surface is changing in time in a periodic fashion. So the time series look like that. So we have regular oscillations, regular in the sense that the frequency is more or less constant. And this can also be seen by taking the Fourier power spectra. So we have well-defined frequencies and harmonics for this signal. The amplitude is not so regular, but in any case, this seems to suggest that we have regular oscillations affected by fluctuations, which in terms of dynamical systems would mean that we have a limit cycle affected by fluctuations. We have different ways of reaching this idea that we have indeed a limit cycle. One of them is to plot the probability distribution of the brightness in a sort of reconstructed phase space. So we take the brightness at 2 different times. So this is like time delay phase space reconstruction. But instead of having just one signal, we plot the probability distribution in this space. And this probability distribution has a specific crater-like shape. And this is characteristic of limit cycles in the presence of fluctuations. So the rim of the crater would be the limit cycle, and the slopes would be deviations from it due to fluctuations. And something else that is also interesting with this technique is that the different parameters can be varied in a systematic way. For example, we can vary the hydrogen pressure, and this shows that oscillations appear only after critical pressure has been reached. So we have zero oscillation and then suddenly oscillations, and very close to this critical pressure, the period of the oscillations is extremely large. And by fitting the points, so for the frequency as a function of the pressure, by, I would say, known scaling laws, we can arrive to the conclusion that what we see is consistent with the bifurcation being a homoclinic bifurcation, since the frequency scales like the inverse of the logarithm of the distance from the bifurcation point. Three things to remember here is that we have oscillations that are more or less homogeneous in space, over 10 to the 5 sides of the surface. We apparently have a limit cycle, and we know how this limit cycle arises, and we know if we are operating close or far from the bifurcation point. And this is really important for the theoretical part, I would say, because when analyzing stochastic systems like stochastic reactive systems, the starting point usually is the master equation under the form that I show here, which is often called the chemical master equation. So one has an evolution equation for the probability to have a given number of particles at time t in a system. And this number of particles can change because of different processes, which are called rho here. So to have the evolution in time of the probability, we sum over all the processes, the probabilities multiplied by the transition probabilities, probability to change from one state to another. And so this is usually the starting point, but getting analytical reasons from this equation is often close to impossible. So what people often do is that they introduce concentrations, which are continuous variables, by dividing the number of particles by something that represents the size of the system, which is here called omega. And this is called the extensivity factor. In this case, nice extensivity factor, excuse me, would be the number of sides on the surface. And doing this, we can change the probability into a probability density function. We can put that back in the master equation, and to the leading order in 1 over omega, the master equation becomes a Fokker-Planck equation, where one has a drift term and a diffusion term. And in both cases, in both terms, one finds probability transitions, and also stoichiometric coefficients, here the nu rho I, which represent the number of molecules that are created or destroyed by the different reactions. And so this is one first approximation. It is valid as long as one is not too close from a bifurcation point. And so it's a good thing that we can know in experiments when we are far away from bifurcation points, so that we can rely on this equation instead of the master equation. Another simplification that we can use is the fact that we have a large number of sites, and large is here 10 to the 5, which is ridiculous compared to the Avogadro number, but large enough so that we can expect the PDF, the probability density function, to scale like the exponential of the size of the system, multiplied by a function which is typically called the stochastic potential. And if we use this approximation in the Fokker-Planck equation, then we get a Hamilton-Jacobi equation for phi 0. Hamilton-Jacobi equation in the sense that we get an equation for phi 0 that looks very much like the Hamilton-Jacobi equation in classical mechanics. And doing that, we also observe that this Hamilton-Jacobi equation has a time-independent Hamiltonian, so it means that one can associate constant energy, so to speak, to this system. But it's not really an energy; it's more like a pseudo energy. And third, we can also use the idea that we observe deviations from a deterministic limit cycle. And in such case, one can try to expand phi 0 around the deterministic trajectory, which is here represented by x star and t star. And by doing that, one rapidly reaches the conclusion that the first terms, the linear terms, are 0, and the first non-zero terms are the quadratic ones. And they involve different coefficients. I will focus on the term that depends on time. So we need just to talk about A and R. So here in this expansion, R is the number of rotations of the limit cycle. And A is something that is related to the pseudo energy that I was mentioning before. More precisely, it depends on how this pseudo energy varies with the period of the deterministic limit cycle. And this quantity, this derivative, is not easy to evaluate, even if you have a very precise model for the system. But in any case, even if we cannot compute how much exactly A is, we reach the conclusion that the probability distribution for the first return times, so this is for R equals 1, is going to be Gaussian because we have quadratic deviation from the limit cycle. And we have an expression for the variance, but at least that is something we can test. So if we place ourselves sufficiently far from a bifurcation point, and given that the system is relatively large, we should expect the first return times of the experiments to obey a Gaussian distribution. So this is something that we tested. And here you have the Gaussian distribution and the data from experiments for different experiments that were done at different pressures and temperatures. So in most cases, the experimental points fall more or less around the Gaussian distribution. There are a few exceptions. Maybe you can see that the green dots, for example, do not agree so well with the Gaussian distribution. But let's say that in about 80% of the observations we had, the first return times were distributed normally. And so this sort of validates one of the predictions of the Fokker-Planck approach, let's say. Something else that can be tested also is the behavior of the properties of the autocorrelation function. I think I do not have to explain to you what an autocorrelation function is, but here is the autocorrelation function for the concentrations. And using the results from the Fokker-Planck equation, and more precisely, the form that we found in the weak noise limit, we can show that this function is actually the product of a periodic function and an exponential that decays as a function of time. And this decaying exponential is actually what controls the decay of the envelope of the oscillations. And in this exponential, one finds TE, and TE here is what we call the autocorrelation time or the correlation time, something that controls how fast this correlation function decays. Putting again the results of the Fokker-Planck equation, we can get an expression for TE. And you see that TE also depends on the derivative of the pseudo energy with respect to the period. And this means that there is a close connection between the decay rate of the autocorrelation function and the variance of the first return times. And we can put this relation slightly differently in a logarithmic way. And so, which is nice with this expression is that by doing this log-log plots, one can verify the prediction of the Fokker-Planck equation solely based on measurements on the time series. Because TE, the average T, the variance of the first return times are all obtained directly from the time series, and you do not need any model or do not need any additional parameter that would come from kinetics or whatever to verify that this is actually correct. And so what we did is do this log-log plot, try to find the best line that goes through these points. The intercept should be minus 2.98, and it's actually minus 2.9, but with the uncertainty, it's okay. And the slope should be minus 1, and we find minus 0.9, which also falls in line with the prediction if we take into account uncertainties. And so this again validates the result of the Fokker-Planck equation. And there are other things that can be done, but I don't have so much time. And so I'll just show you one or two things that can be obtained, but by postulating a mechanism for the reaction. So, for example, if one has a mechanism for the reaction, we can sort of fit the autocorrelation function with a stochastic model. And so here what you have is in blue the experimental autocorrelation function, and in black you have the theoretical autocorrelation function that has been obtained here with Gillespie simulations of chemical movement. So if they match pretty well, and also one can reconstruct what I was showing you before, which is the distribution of probability of observing a brightness. So on the left-hand side, you have this distribution from the experiments. On the right-hand side, you have the distribution from, again, Gillespie simulations of the model. And so this seems to confirm that the stochastic theories capture a lot of, I would say, the fluctuation-induced properties in this system. And so to summarize, so nonlinear phenomena such as oscillations can show up at the nanoscale, but obviously they are affected by fluctuations. And we could verify a few theoretical predictions on the time series from the experiments, like the Gaussian distribution of the period, the scaling of the correlation time, also the shape of the correlation function and the stochastic crater. And I mentioned on several occasions that I couldn't speak about everything, and we also verified some predictions concerning the effect of fluctuations on multiperiodic signals, on excitable dynamics, but we still need to find an example of how to study experimentally low-dimensional chaos in that sort of systems. And I will just leave you with a few open questions if you're interested in that sort of things. Possible extensions, like can we use the experiments to propose scaling laws that go beyond, I would say, what we have done, so staying far away from the bifurcation point, for example. We still need to explain exactly how it is that the surface is homogeneous during the oscillation, because the oscillations are rapid. This means that there is a rapid mixing at the level of the surface. And other questions that could be of interest is the controllability of these dynamics with external control means, and also maybe the analysis of different physical-chemical properties. I mean, there has been a whole development of stochastic thermodynamics recently. Maybe some of these predictions, or some of the predictions of this stochastic thermodynamics can be verified with the sort of approach that we have been using. So with this, I would like to thank you. I hope I was not too long. I think a little bit too long, but I will be happy to answer questions now, if there is any. Thank you.
Thank you very much, Yannick, for your excellent talk. I think we have time for one or two short questions. The first question that popped up in the Q&A was asked by Jan Sieber. Are the time-space scales in these experiments such that real-time feedback control is possible?
Oh, yeah. But that's exactly what I was saying. It's one of the things that we would like to do at some point. There are systems where the oscillations are not so fast. So you have something like a few minutes between two oscillation peaks. That suggests that we could maybe try to use something like a control by the electrical fields. I mean, the temperature is difficult to change because there's such an inertia in the system. The pressures, it's comparable. So if you change the pressure externally, it will take forever before the pressure changes at the level of the sample. But maybe using the field would be something or that could be done, or maybe using something external. At some point, we're thinking about using lasers that could even, in some cases, destroy the sample. So yeah, in principle, I think it can be done. In practice, I'm not so sure.
Okay, maybe we pick one question of somebody else from Domenico Lipolis. How can you tell it's a limit cycle? Experiments say it's periodic and it's got to be stable to be observable, but is it asymptotically stable?
But from the time series, I would say it's very difficult to say. I mean, when you look at the experiments and what I was showing, it would be more honest maybe to say that we hope it's a limit cycle. But now the signs that it really is would come from the modeling that I was mentioning in the end. So one can construct a chemical model for what is happening. This chemical model reproduces pretty well the shape of the autocorrelation function, for example, and the shape of the current and brightness signals. And so this model has a limit cycle. And so indirectly, I would say that would be another sign that there could be a limit cycle in the system. But defining a limit cycle from experiment, I'm not even sure if it is straightforward to define the equivalent of a limit cycle for stochastic systems. So how do we define asymptotic stability in the presence of fluctuations? I think it's not trivial. But indirectly, that would be a sign that it is a limit cycle.